Hello, my name is Luisa, and I'm here to present the approach I have been working on with Augusto and Aura to facilitate lung region segmentation problem in chest X-ray images through image processing techniques. So our goal here is to go from a chest X-ray image and figure out the corresponding binarized image, which we called the segmented lung image. Some of you might be asking why this is important. Well, first of all, radiographic images are an indispensable tool regarding clinical investigation for physicians worldwide due to their speed, convenience, and simplicity. Secondly, we can say that lung segmentation is one of the most critical radiographic analysis tasks due to the variations in opacity in the lungs, making it a complex region to segment. Furthermore, authors such as Raman, Teixeira, Bassi, and others point out that using the segmentation as a pre-processing step to neural networks improve the performance of classification problems for identifying diseases such as tuberculosis and COVID-19. And finally, as we are going to see, the majority of the methods used in the literature to segment lung region end up using neural networks, which adds even more complexity to the problem, leading to a long time to train and the dependence of a high number of images to be trained with their respective ground truths. Thus, this paper aims to address a second issue. Is it possible to produce similar results based on less computational cost methods? Because besides the necessity of investment in equipment that's not viable for many hospitals and clinics worldwide, there is a known trade-off between machine learning algorithms and their impacts on the environment. There are several studies that automatically detect our region of interest on CSR images, mainly using variations of convolutional neural networks, and in those studies, limitations highlighted by the authors include the amount of time for training their models and the necessity of powerful machines. Another challenge faced by such studies is the necessity of a high number of images pre-evaluated by a specialist. Well, when it turns to medicine, finding complete and adequate databases can be really challenging because to produce a great dataset, it's important that it's balanced, which means that the number of samples for a positive or abnormal group is expected to be almost the same as other groups. And we also expect to have diagnoses from different specialists to improve generalization, and that can be costly in medicine. In terms of the imaging processing technique used for solving the lung region segmentation problem, we identified the study provided by Saad and other authors that proposed a method based on Kenny filter and binarization, followed by morphological operations such as dilation and erosion. But Ken edge detection algorithm is complex, time-consuming, and high hardware cost. In our previous work, we considered the usage of morphological operators applied after binarization. Different from the current method, both Saad and our previous work considered morphological techniques applied only after the binarization of the images. And in the here proposed approach, the morphology operations are used before and after binarization to capture more details of the gray tones and facilitate the region of interest identification. To compose our dataset, we considered a qualitative evaluation of our team's specialists, respecting the ones that would better compare with previous works. We chose 12 images from the Japanese Society of Radiological Technology, the JSRT, and 12 images from the Shenzhen Chest X-ray, the CHN. To evaluate our approach, we opt for not using ground truths automatically generated because once they are not 100% correct, they could lead to a false evaluation perspective. Therefore, the radiologist of our team manually created GTs for the images that we used. All images and the respective ground truths are available for download on the QR code here. Regarding the JSRT dataset, there is a lung segmentation data kit which contains GTs provided by specialists. In this case, we evaluated the proposed method considering both the GTs created by our team's specialists and the Cyrus one. The main idea of our method is to define areas in the CXR that are not relevant for the region of interest. So we start receiving a CXR image and identifying areas that must be eliminated, like the trachea, any part out of the patient's body, and some other neck region. That is relevant because those regions present similar tones to the region of interest, and not eliminating them jeopardizes the binarization process. In the sequence, we apply the mask of the pitfalls identified to the input image and apply some exposure corrections to binarize the result. Finally, we use some mathematical morphology operators to remove noise and promote impaired areas caused by binarization. Now we are going to pass through all the steps in a bit more detail. The first one is the one that actually contains the highest number of steps inside, that is identifying pitfalls. Well, on this step, we want to eliminate any region that's out of interest. So we produce a mask, a binarized image. The first tasks will involve the identifications of areas that are out of the patient's body, like here and here. And we do that by applying a morphological reconstruction by dilation to the input image based on an edge marker. We can see that the patient's body will become darker, and if we apply a sigmoid function, it will become even darker. That facilitates the binarization process, and we can use erosion to improve the generalization of the mask. The next step is to eliminate the trachea region. But to do that, we do a sweep from the left to the right side and from the right to the left on the upper part of the image until we reach a foreground pixel, meaning that we found the extremities of the neck, and if we get the center of it, we are going to find the trachea region. If the trachea region found by the algorithm is out of the center in more than 20%, like here, for example, the algorithm will not consider eliminating the trachea region. And it's only going to jump that step and go to the next step. On the next step, we want to remove any noise that appear close to the neck region. So we apply the mask that we produced until now to a reconstruction of the reconstructed by margin image. Here we apply a markup that considers the expected position in which we will always find a silhouette in a CXR image. That position was considered through observation based on the data sets that we chose. To identify the neck, we apply a histogram projection on a vertical axis, so that when the tone curve starts rising, that means that we are starting to reach the patient's body, the foreground pixels, and then we can remove any part of the image before that. The next step is to binarize the image. Nonetheless, even after removing pitfalls, it is important to adjust some gray tone levels to enhance the contrast of the region of interest due to the noisy nature of the CXR images. Instead of enhancing brighter tones of the region of interest, we opt to enhance darker areas values. So the first task of this step consists of inverting the input image, adjusting it by a sigmoid function, and morphologically closing it. The next task is to revert the image to its original tone scheme and remove any values of the edge of the image. Finally, the image's binarization task is done through local adaptive thresholding, in which each pixel receives a threshold value based on the sum of its neighborhood values weighted by a Gaussian window. After binarization, some remnants out of the region of interest are still visible, so we apply some morphological techniques to remove that noise. We start applying a simple opening morphological operation to remove disconnected areas. Additionally, as some images presented small portions of areas inside the region of interest as a background pixel, we apply the remove small holes function of the scikit image package to turn them into white pixels. And the last task of this step is applying a conditional dilation, because the cardiac region here is already well defined by the binarization process, but the ribs area, like the ribs edge area, is normally jeopardized during the binarization. So we apply the dilation only on the expected rib edge based on the position. Regarding the results of the method, we can see here the obtained segmented lung image from our approach, the respective desired or ground truth image, and the difference between the segmented images. We can observe that the method produced a good approximation for this case. Now let's see these evaluation numbers. As I said in the beginning of the presentation, as our ground truth source for the JSRT database, we considered both the one produced from our specialist and the one provided by SARU. This evaluation demonstrates that the GTs provided by our specialist is similar to those provided by SARU. To evaluate how adequate our method is regarding the relevant area, that is the lung region, different from other studies, we propose using the specificity measure, because through this measure we calculate the proportion of background pixels that are correctly classified. By doing that, we can say that our approach classified a non-region of interest area correctly 92.92% on average. Cow and Zhao's study presented a specificity of 98.8% for the JSRT dataset, with an average running time of 44.38 milliseconds. For the same dataset, our method's specificity is 93.4% and takes an average of 0.0006 milliseconds to run the whole process, including the loading for one image. Just for better comparison, the radiologist of our team took an average 40 minutes to produce each of the GTs used to evaluate our method. To conclude, we can say that this paper presents a method based on image processing techniques for region of interest segmentation in CXR images, and it serves as a pre-processing step for more complex analysis, which involves diagnosis classification problems for identifying tuberculosis, COVID-19, and other lung diseases. In terms of future improvements for the presented approach, we can state that the lateral lung regions are visibly more challenging to delimit once they present a high overlap of adjacent tissue, including ribs edges. Also, future works related to adjusting and rotating not centralized images and removing patient tags are highly relevant for greater generalization of the method proposed here. And other future analysis must include a qualitative approach from a medical group to evaluate the segmentation results and this method usability in the clinical context. If you want to access the ground truths, our code, and the images selected, they are all available for download on the QR code here. And if you have any questions or comments, feel free to contact us through the emails provided here. That's it. Thanks for your time.